Okay, so welcome to class for Thursday, April 23rd. Um, in terms of the schedule for today, things we need to do, I wanted to come back and talk about the 2D histogram that we were talking about last time with our little sample Monopoly game thing. And I wanted to talk briefly, just sort of briefly touch base on how posters are going. And yeah, and then we'll be done hopefully a little earlier today than normal. Let's do posters first. How are we feeling about posters? I know I've talked with a couple of groups and people are feeling, I think, okay, but I wanted to check in.
I mean, I've started it and just trying to get figures. Yeah, I'm having a little trouble getting it to go turbulent again, but other than that,
Okay. What does it do, Blake?
it just kind of flows through the box, about what you'd expect.
Okay.
Yeah, I was trying to hopefully get like those little coils and such in there, but
So do you see anything going on at the edges?
yes.
Okay. So it is feeling the edges or the walls, right? I mean, it is.
Yeah, I tried cranking down the Reynolds number, or no, cranking it up, sorry, by putting the viscosity down, and that didn't really seem to help very much.
Okay. So we'll have to look at that. The pipe flow is a problem that so what we're doing is basically pipe flow, right? It's flow between two layers, and it has been studied to death, and I have systematically ignored it because it turns out in astrophysics you don't often have pipes. Go figure. But engineers have studied pipe flow to death, so I can do a little bit of looking up. Okay, but you've got.
Yeah, it seems to work though, which is, I
It
guess.
runs. That's nice.
Yeah. Yeah.
Cool. Okay. So I think the poster that's probably the furthest along, just from looking at what people have shared, is the traveling salesman guys. I mean,
yeah, we're doing good.
great. Good. And then the Galaxy people, we were just talking before class started, but Bjorn was saying that Cindy's got something, but we haven't actually seen it yet. So, okay, well, I'll let her know. With the posters, do have a read over them. I would like to see them before you submit them. So if you can share them with me. Saturday is going to be, unfortunately, a very busy day for me. I'm going to be installing sod, which, if that doesn't sound like fun, I don't know what does. But Friday afternoon, probably, if you could get me something that is something close to a complete draft of a poster by about like 2:00 on Friday. That way I can give it a look over and give you some feedback. And I just dropped the links to the Traveling Salestronaut poster and the Canopy Waves poster in the Advanced Comp Spring 20 channel on the Slack channel. So if Bjorn or Cindy or whoever could drop that in for the Galaxy group too, that'd just put them all in one place and make them easy to find. So. Okay, let's see here. Anything else? Questions, comments, concerns? I'll just add one more thing, not directly on the posters, but on the recordings. As I said before, I think the best way to do these recordings is to get all 2 or 3 of you on a Slack channel, on a Zoom call, and then somebody hit record and do the presentation that way. That way you can all be speaking. You can, say, I'm going to talk about the introduction. You're going to talk about the, background, whatever. And don't read the poster, but, act like there was somebody you were presenting to, who, you're explaining what you're doing, explain the plots. Basically, my advice for presenting a poster is what you basically want to do is talk through the pictures. So for each plot, explain what it's an image of, explain the axes, explain the units, explain how you got the data points on it, or how whoever got the data points on it got them, and explain what it means, right? So for example, I'm actually going to pull up the canopy wave poster here, and I've got it right over here, and share my screen. Okay, so can you all see this is the canopy wave poster. Can everybody see that?
Yeah,
Yeah.
that's good.
Okay, so what I would suggest doing is, zoom in. I don't know what the right level of zoom is, but zoom in so that in the video, what you're talking about is big, right? So for example, this image right here, you might say, this is an image of clouds showing a Kelvin-Helmholtz instability, right? So what's happening here is that you have wind that is flowing to the left on the top and to the right on the bottom, and these clouds are kind of stuck in the middle. And what they're doing is they're making these characteristic rolls, right? They look like cresting waves, but it's really this rolling up of this material as these two layers interact with each other, right? And you might then lead that into Kelvin-Helmholtz instabilities are, as the name implies, unstable. And so what they'll do is they'll start off on a small scale, and they'll grow and they'll grow and they'll get bigger and more vigorous until eventually they will result in just turbulent mixing, and it'll just mix up the whole interface. That's what Kelvin-Helmholtz classically does, right? And so what you're doing there is you're telling them, okay, what are you looking at? Then you sort of walk them through the thing. You tell them, and then you tell them why it is that you showed them that, right? So in this case, they're looking at a photograph of clouds exhibiting Kelvin-Helmholtz rolls. We talked about, what is actually happening here. You have high velocity on the upper layer, low velocity on the bottom layer, or backwards even. It could be to the left. We don't really know. But that, and then you had a interface between the two. The Kelvin-Helmholtz instability generates these roll structures, and then you talk about what what will happen in the future of this photograph, and then you talk about why, right? And then that leads into this discussion of canopy waves may not actually be waves, right? These Kelvin-Helmholtz rolls they're not a wave, right? There's not a traveling motion here. But they do have a sort of wave-like appearance. And so maybe that's what we're seeing with canopy waves. The trick is the canopy waves don't grow in time, right? As you see this pattern develop, it doesn't get bigger in time and then eventually go away, right? On a Kelvin-Helmholtz instability, it should grow and get bigger and bigger until eventually it all just gets ripped apart by a bunch of turbulent mixing, and you don't end up with any structure. Okay, so does that make sense? That sort of strategy for talking through images?
Yeah.
Yeah,
Okay.
sounds good.
All right, so that's what I recommend on your video is you just basically jump from, image to image and explain what it is people are seeing. That's also true if you're going to put any math in there, right? If you're going to have a formula, which is not a bad thing to do at all, but you have to treat it as if it's an image, right? So you have to tell people, walk people through it, tell them what they're looking at, explain to them the pieces of it, explain the notation, and then tell them why you showed them that. And why, saying, well, this is the equation we solved. That's not telling them why you showed the equation. That's telling them what you did with it. But with the why is, well, because this represents the trajectory a object would take in the solar system, experiencing all of the planet's gravitational fields. Okay, so that's enough of that. Let me stop sharing that thing and start sharing this thing. Okay. Nope. Nope. Okay, so last time we talked about probability distributions, the two-dimensional probability distributions, right? And what we did is we went ahead and generated a 2D probability distribution function for our Monopoly simulator, right? Where one of the variables was how many spaces did you move, and the other one was how many times did you roll doubles. And if you remember where this landed last time, we had made some plots, but the plots were kind of hard to see, and they seemed to be missing some information. It just wasn't a good way to display it. So I poked around a little bit, and it turns out that, as is almost always the case in Python, there's already a way to do this, okay? So the way to do that is right here. Is this there inside of matplotlib.pyplot, there is a function called hist2d, just like there was one called hist, okay? And it'll actually return stuff. So I'm going to call it temp. And ignore this for a minute. That's me playing with something. Okay, so if we run it now, this figure will come up, and what happened to my figure? Okay, I've got too many figures now. Here we go. This is the right figure. Okay, so what you're noticing here is that this made a histogram, a two-dimensional histogram, right? And it goes from 3 to 36 and from 0 doubles to 3 doubles. Okay, obviously there's some issues here. What do you notice about this?
It's horizontal, and there's like space in between, the histogram bars that's just dark.
Yeah, so there's something weird going on here, right? Like this bin goes from 0 to, it looks like about 0.3, right? And then there's these empty bins, and then there's another one that's got something right here. It's very dark, right? You'll also notice that this bin goes from 3 to 6, and then the next bin goes from 6 to 9, and the next bin goes from 9 to 12. So maybe not the most useful bins, right? So we're going to have to help it out a little bit. And we can do that a couple of different ways. So the first thing I want to show you is the 2D histogram has a normalization function, okay? And the way you do it is you say norm equals, and then this mcol is actually imported. So it's in matplotlib.colors. Okay. And what this is there's a whole package inside of matplotlib that has to deal with how you treat colors. And there's a function in there called power norm. What power norm does is it changes the spacing on the colors, right? So if I do a power norm of 0.5 instead of a power norm of 1, we'll see something interesting happen here. Okay. So what changed? It'll help if I make it bigger.
Well, you can actually like see all the columns now, or I guess rows in this case.
Right. Why?
Uh, the color bar is like not just linearly scaled anymore. It's like, it looks closer to something like a logarithm.
Yeah, so what it's actually doing is it's using a power law. So instead of linearly spacing the colors, right, and the way it does this is...
Not really weird.
Sorry, what was that?
I'm not sure if I'm the only one that's experiencing it, but is Dr. Nelson sound kind of like weird right now?
Yeah,
That's fine.
Agreed.
like a robot.
Well, I'll try to be less robotic in the future. So what's happening here is instead of linearly corresponding colors, right? Because the data here goes from 0 to about 36,000. Okay? So what normally happens when you do like a p-color plot is it looks at the range of your data and it makes a map that takes your data and maps it to an integer between 0 and 255. Are you guys getting any of this? Am I completely roboticized?
It is so roboticized. Like if I can be very honest, Dr. Nelson, you sound like you could be voice acting an evil villain for a cartoon. An evil genius, I should add.
Let's see if this helps at all. If I turn off my video, does that help?
Nope.
No, it doesn't. I don't think it's an internet thing. I think it's like, I don't know. It sounds like as if like you're like, I don't know, like as if like, I don't think you're using a microphone, or are you using a external microphone or one that's like built into your computer?
Okay, I just switched microphones. Does that help at all?
Oh my
Yeah,
goodness.
it
Yes.
sounds great.
Okay, good to know. Apparently my headphones were having an issue.
It be like that sometimes, Dr. Nelson, and it's okay.
Yeah. Okay. All right. So, okay. So what I was trying to say here is that normally what a plotting routine like p-color does is you give it some data. Let's say your data goes from 0 to 100. Okay. What it will do is it will create a linear map that chooses bins of your data to map to integers between 0 and 255. And the color table you choose will determine what color is represented by, say, any given number, 236 or 174 or the number 6, right? What this power norm does is it changes it. Instead of being a linear mapping, it maps it as a power law. So in this case, a power law, this is mapping like the square root. So that means that the bins that it maps data into are changing. And we can even change it further, right? I could come down here and make it the 4th root and rerun the thing. and voila, you'd see it even better, right? What I'm doing is basically expanding the bottom of the color table and compressing the top of the color table. Okay, so that solved one issue, but it didn't solve the other one, and that is that the bins this thing has chosen for me are not necessarily the most useful bins, right? And so let's help it choose some better ones. If I come over here, much the same way I did before, I can choose bins, okay? And in my bins, if I look over here at the help page for it, right? It says bins can be any number of things, right? If it's an integer, it will be the number of bins, right? NX and NY will both, the number of bins in the horizontal and the number of bins in the vertical axis will be the same. If I give it two sets of integers, it will give that number of bins in the X, the second number of bins in the Y. So that's what I want. I can also specify the bins, okay? But for now, let's just do it the way it wants. So I want 34 bins in the X of the way this thing is plotting, right? Because there are 34 possible roles. And I want 4 bins in the Y. So let's tell it that and see how it goes. So I'm going to come down here. I'm going to say bins is 34, 4. And let's see what it does. Now, that is more like what we actually wanted, right? Now, our bins actually represent where our data is. Now, they're still a little bit odd because it made 4 evenly spaced bins. So the first bin goes from 0 to 3/4. The second bin goes from 3/4 to 1.5. The third bin goes from 1.5 to 2.25. And the fourth bin goes from 2.25 to 3. So visually, these bins aren't sitting where we might put them normally, right? But it now is representing our data the way we wanted to, right? And so we can actually see what this thing is doing. And we can start to see some interesting things. Like, for example, wait a minute, there's something weird here. I only went to 35. I went from 3 to 35. Why did I go from 3 to 35? Oh, maybe I never rolled a 36. Okay, let's make it, let's try 400,000 rolls. Because the odds of rolling a 36 are actually not very good at all. Ah, there we go. Now I rolled a 36. So now it's doing what I think it should do, right? Okay, so there's your two-dimensional probability distribution function, right? We've got the probability of rolling any given number, right? Well, not quite, because actually this is still a histogram, so we would need to normalize it. And if we look back over here, we can see that if we say density equals true, it will normalize our histogram. So let's come down here and say density equals true. And I probably should make this on more than one line, but I'm not going to at the moment. And there we go. Now it's actually a PDF, right? Now it's actually a probability distribution function. If I integrate over both axes, I'll get 1, right? Meaning the probability of everything, right, is, or if you add up all the probabilities, you get 1. Now I can do some interesting things with this. As we talked about it last time, we can calculate things like marginal probability distributions. So we could say, okay, if I roll a 7, what are the odds I rolled doubles, right? And what that basically is saying is, okay, look at 7, and we're just going to take out a slice here. There we go. So I'm just going to take this slice, right? If I rolled 7, there's no chance I rolled 3 sets of doubles because it's not an even number, right? There's a very small chance I got 2 sets of doubles, meaning I rolled snake eyes, and then a 3. There's some chance I rolled 1 set of doubles because I could have either rolled 2 1s or 2 2s. But most likely I just rolled once. Okay? And we can play these games. We can also now, from this data, we could say, what are my odds of rolling doubles? Right? I could sum the probability distributions over the number of spaces moved and just get the probability of rolling 0 sets of doubles, 1 set of doubles, 2 sets of doubles, 3 sets of doubles. And I can ask all kinds of questions like that, right? What is the chance that I go to jail, right? I go to jail if I roll 3 doubles. So I would just add up all these guys. So does that make sense? This gives us a lot more information to play with, right? If we have this 2-dimensional distribution, we can always get the 1D distribution back. But if we've got the 2D distribution, now we can start poking it in all sorts of different ways, right? So let's think of a common thing that happens in Monopoly. In Monopoly, most of the properties are arranged so that there are a group of 2 of them together, 2 of the same color, and then there's a space, and then there's 1 next to it, right? And so if you're playing Monopoly, you want to, say, avoid those. So now what you could do here is you could say, okay, I'm on the railroad right in front of the, the yellows. If you can imagine a Monopoly board. I don't know how much you guys have ever played Monopoly, but I want to, or I'm on free parking. I really don't want to land on the yellows. What are my chances of landing on a yellow, right? And then I could say, okay, to do that, I'd have to roll a 6, a 7, or a 9. So what are my chances of getting a 6? Well, I just add up these guys, right? Or a 7, I'd add up those guys. Or a 9, and I'd add up these guys. And I would also have to think about what are my chances of getting a 9 that also involved me going 7 spaces first, right? So the chances of doing this, rolling a 7, and then rolling snake eyes, right? Rolling 2 1s. Because then I would hit the yellows twice. So anyway, does that make sense? We can start to build out, now we have the information, we can build out the probability of any specific event or sequence of events that you want.
Yeah, it's pretty cool.
So in theory, right, you could build this for any kind of setup, right? Now, in practice, you don't want to do that. In practice, you probably don't want to, have an infinite dimensional probability distribution function to tell you about Monopoly. But you could, right? You could keep building this probability stuff. And by adding more possibilities, all you're doing, or more axes, right? More dimensions on your probability distribution function, you're just giving yourself more information. You're never giving yourself less, because you can always recover what you had before just by integrating out the dimensions you don't want. Okay, Questions, comments, concerns? We feeling good about this? Okay. All this will be fun because on Monday, or I'm sorry, Tuesday, we're going to start in on what you can actually do with any of this. And some of these Monte Carlo techniques that will allow us to do some analysis, uncertainty analysis, hypothesis testing, this sort of stuff. Okay, so I think we're probably good for today. Any questions in general? I apparently need to clean out the connection for my headphones.
It could have just gotten like unplugged like halfway or something like that.
Yeah, that might be it. I suspect it's the connector. This is getting off topic, but I figured out a while back. So my phone was having the hardest time with my headphones. I'm one of these crazy old people who like cords. So these are my headphones of choice, right? These lovely little earbuds, and they were having such a hard time with my phone. And I actually went and cleaned it out, and there was I don't know, an amazing amount of lint in the USB-C jack on the bottom of my phone. So I suspect there's probably something in there because they've been used heavily over the past month. So, all right. Well, I think we're good then. Let me shut down the recording, and I'll stop sharing my screen here. And I'll shut down the recording, and then I can stick around and talk to the Galaxy people. Okay, did Cindy ever show up?
She was here before I was, Dr. Nelson.
Yeah, I was here.
Oh, there's Cindy. Great.
Hi.
Hi. All right, I'll turn off the recording.